Very good afternoon to one and all students. Am I audible and visible? I have launched a poll. You can give your answers over there. So just let me know if I'm visible and audible to all of you. Yes. Good afternoon, Agam, Jamie, Tinsukia, students, and Rudransh and Bangtoi. Good afternoon to all of you. Okay. So now coming to the class. So we are in thermodynamics lesson, right? So yesterday we have studied the basics of thermodynamics and later on I moved on to the first law of thermodynamics, right? So under the first law of thermodynamics topic, we have covered the internal energy and the law of conservation of energy yesterday, right? And the first law of thermodynamics formula also we have derived. So what is the formula? Can you tell me the formula of first law of thermodynamics? It is delta U is equal to Q plus W, right? So this is what we have derived. And coming to today's session, we are going to start with the work. Okay, and we have 5 more topics under this first law of thermodynamics. Now let's do that. So coming to the work, so what is work actually? It is the energy exchange between the system and surrounding against a constant external pressure leading to volume change of the system. Okay. So we may have a container. Okay. And there will be some gas molecules or some other particles. Okay. And if I keep a piston over there, piston is the instrument which is used to give pressure. Yesterday I have told you, right? And if I give some external pressure from outside on this system, so what will happen? There will be volume change. So what will happen in this case? If the external pressure which I am giving is more, then the compression of the gas will happen. So which leads to the volume change. So this is the initial volume. And if the external pressure is more compared to the pressure of the gas, so the gas molecules will come closer to each other. Okay, will come closer to each other. And this is the final volume. So it is leading to the volume change of the system. Okay. So this is the initial state and this is the final state. So there is some energy exchange between the system and the surrounding against this constant external pressure which I am giving, and that leads to the volume change. So this is called as work. This is called as work. I am doing some work on the system. Okay, that is called as work, which is actually the mechanical work also we can say. And this work has 2 types. Okay, expansion, it can be classified into 2, expansion and compression. So when do we call the expansion has occurred for a particular system? If the internal pressure is greater than the external pressure, gases will expand against a constant external pressure and we call that as expansion. Okay, so here let me take the same system in which I have the gas molecules, okay, and the piston is attached to it. The pressure which I am giving from outside is called as external pressure. Okay, there will be pressure already present inside the system. Okay, ideal gas will have some pressure which is called as the internal pressure or the pressure of the gas. This is called as the internal pressure or the pressure of the gas. So if the pressure of the gas is more, if the pressure of the gas is more, then we can say that the gas is doing the work. So in that case, if the gas does the work, what will happen? The piston will go up and That is called as expansion. Gases are doing some work. Okay. So in that case, expansion will occur. Got it? And what is compression? External pressure will be greater than the internal pressure. The pressure which we are giving is called as external pressure, right? So if that is greater, so in the previous case I have shown you here, right? So if the external pressure is greater, then the compression will occur. So these are the two cases under the work. Okay. Now we'll go for the sign convention of work. So let's see. In case of compression, what is going to be the sign of work? And in case of compression and expansion, what is going to be the sign for work we have to use? So first of all, coming to the compression case, in case of compression, initial volume will be greater. Okay. So here we have the picture, right? So here we have the picture. You see here. Initial volume is greater than the final volume. Okay. So V2 minus V1 will come out to be negative. My voice is not audible. What about other students? Hi Anki, Inu. What about you guys? Am I audible to others? Yeah. Agam, please check your speaker. Check your device. Okay, okay. I'll do a little bit loud. Fine. So in case of compression, the final volume is less than the initial volume. Okay. So V2 minus V1 is negative. And yesterday I have given you that W is equal to minus P external V2 minus V1. So this is the formula to find out the work. Okay. So if V2 minus V1 is negative, so negative into negative will be positive, right? So W value will be positive in case of compression. Okay. So work done will be positive in case of compression. So if the work is done on the system, then the sign will always be positive. So we are doing the work on the system, right? So it is positive. Next, coming to the expansion case. In case of expansion, this is the initial volume and the internal pressure will be there for the gas. And if the gases are doing the work, what will happen? Expansion will happen. Okay, expansion will happen. So in that case, the gas is doing the work. So the work is done by the system. If the work is done by the system, the W value will be negative. Okay. So if the work is done on the system, if the work is done on the system, then the W value is positive. And if the work is done by the system, then the W value will be, then the W value is negative. So this is what you have to keep in your mind. Okay. So yesterday we have studied for heat, right? If the heat is entering into the system, then in that case, Q value will be positive. If the heat is coming out of the system, it will be negative. So the same thing is followed here. So like heat, we have to go for work also. Okay. So I hope this is clear to all of you. So any doubt from this part for anyone? Is everything clear? The sign convention and the types of work and the definition. Everything clear? Okay, very good, Rakshita. Yes. Thank you so much for your responses, students. So now we will go for the formula for expansion of work. Okay, so the same formula which we have seen in the previous slide. So for expansion, you have to use W is equal to P external V2 minus V1, which is a very, very important formula. Okay, so all of you please note down this formula and we will use this formula for solving many questions. Okay, for solving many questions, we will use this formula. Okay, Now let's go for the types of work. We'll go for the types of work. There are two types of work. One is reversible and the other one is irreversible work. Okay. So now I'm going to give you the pressure volume graph for these two works. Okay, you all know what is reversible, right? If one is going back to the other form and if A is giving B and B is again giving A, then it is called as reversible. Irreversible means A will go to B, but B cannot come back to A. So that is called as irreversible. Okay. So now I am going to give you the pressure volume graph for this reversible and irreversible work. Okay. Now let's go for it. PV graph for types of expansion work. So first of all, for the reversible, if you see, we have initial pressure for the system and the final pressure. Initial volume we have and the final volume we have. So as the time increases or as the volume increases, the pressure is decreasing. As the volume increases, the pressure is decreasing. So this is in case of reversible. Okay, both the initial pressure, final pressure, initial volume, final volume will be different. But in case of irreversible, volume will change. Volume will change, but the pressure remains constant. The external pressure remains constant. Okay, so this is the graph we get for the constant pressure because the pressure is constant, right? So we will not get a curve. Okay, so we will get an area like this under the PV. Got it? So now I'm going to ask you a question. In which case, the area under PV curve is more? In which case, in reversible or in irreversible, the PV curve, the area under PV curve is more. In which case, the area is more. Can you tell me whether it is in reversible or irreversible? Very good. It is reversible. Okay. So there is one relation. So that relation is very important. All of you note down that. Okay. So if you want to find out the maximum work done, you have to look into the area under the PV graph. Okay. So area under the PV curve is directly proportional to the work done. Okay. The maximum work is done in which the area is more. Got it? So using this relation, we have got one previous year question in the exam. Okay, so all these things are very important. Please note, have a note of it. Clear? So now moving forward with this concept, we will solve one question. Okay, are you all ready to solve a question? Are you all having the notebook and pen with you? Shall we solve the numerical? We are going to solve a numerical, the problem. How many of you are ready? Agam is ready. I hope all of you are ready with your notebook and pen, okay? And I hope all of you are noting down the points which I am showing you on the slide and which I am saying, right? I can have a hope on you guys, right? I'm having the hope. Yes, okay. So now let's go for the question. This is the question. In a process, 701 joule of heat is absorbed by the system and 394 joule of work is done by the system. What is the change in internal energy? So what is asked? We have to find out the change in internal energy. What is meant by internal energy? U. Change means delta U. So delta U we have to find out. Okay. And 701 joule of heat is observed. 701 joule of heat is observed. So heat is observed by the system. So before moving on to the problem, let me show you a picture. So here you see, so this is a container and we have gas molecules here, ideal gas molecules here, and a piston is attached. All of you can able to see the piston, right? So this is a piston which is used to give the pressure. If the heat is entering into the system, then the Q value will be positive. If it is coming out of the system, Q value is negative. In the same way, if the work is done by the system, expansion will happen. In that case, W is negative. If the work is done on the system, this is on the system and this is by the system. Okay. And here heat is entering into the system and here heat is leaving the system. He enters and leaves. So if the work is done on the system, W value will be positive. So this is the cylinder which has the ideal gas and these are all the parameters we have. Now what is the given value? 701 joule of heat is absorbed by the system. Absorbed means it is entering into the system, right? So what should be the value of Q? It should be plus. So it is plus 701 joule. And coming to the work, 794 joule of work is done by the system. So if the work is done by the system, W value is negative. So the answer should be, the value should be minus 394 joule. Q is equal to plus 701 joule and W is equal to minus 394 joule. Is it clear up to this? Now using the first law of thermodynamics, all of you can able to find out the change in internal energy, right? Delta U. Very good, Tinsuki asked. Very good. So according to first law of thermodynamics, delta U is equal to Q plus W. Just by direct substitution, you will get the answer. 701 minus 394 is equal to 307 joule. So the change in internal energy is 307 joule. Very good. Shall I go for one more question? Is this question clear? Do any of you have any doubt here, students? All of you have done this on your notebook? Okay, so now I'll go for the next question. Okay, if you need some time to copy the question or copy the concepts which is there on the PowerPoint presentation or on the slide, you can ask some time from me and you can copy it. Okay, so don't just listen the class without understanding or without noting down the important points. So please ask the time from me if you need it. Clear? So now I'll go for one more question for you. So which type of expansion work, reversible or irreversible, is greater? And you have to tell me why the particular work is greater. So answer is very easy, right? So just before few minutes, we have discussed this. Which work will be greater? Reversible work or irreversible? Yes, the answer is reversible. Reversible expansion work is greater than irreversible. Okay, because according to the pressure volume curve, the area under reversible PV curve is more. So that's why that first one is the answer. Very good. Now let's go for the next topic, expression for work. So here in this topic, I'm going to give you 3 formulas and all the 3 formulas are very, very, very important. Okay. So now let's go for it. Isothermal expansion of an ideal gas. What is meant by isothermal? Yesterday we have seen, no? What is meant by isothermal? Can anyone tell me what is meant by isothermal? Temperature is constant. Iso means same. Iso means same and thermal means temperature. So if the temperature is constant, then it is called as isothermal. Okay, isothermal expansion of an ideal gas is the topic. And here temperature is constant, which implies delta U is equal to 0. So I will tell you in the upcoming slide why delta U is 0 if the temperature is constant. Okay. So I'll tell now itself otherwise so that you can understand these two. So now here listen. Delta U is equal to NCV delta T. So this is one formula which we will discuss in the later part of this lesson. Okay, so this is one formula. And here, if the temperature is constant, delta T is equal to 0, right? Yesterday we have discussed under the types of the proper process, no? We have studied 5 types of process. And in case of isothermal case, temperature is constant. So delta T will be 0. So if the delta T goes to 0, 0 into anything will be 0. So here delta U will be equal to 0. Then that's how we are getting this relation. Okay. So now according to the first law of thermodynamics, this is the formula for delta U. And here if I substitute delta U is equal to 0, W will be equal to minus 2. W will be equal to minus 2. So these are all the points you have to keep in mind regarding the isothermal expansion. Now, if the case is reversible, then the formula to find out the work done in case of reversible processes minus nRT Ln. It is a logarithmic function. Okay. Ln V2 minus V1. Okay. If you are converting this into log, then you have to multiply this by the number 2.303. Okay. 2.303 into nRT log of V2 by V1. Okay. So, if you are keeping this as Ln, then you have to use this. If you are converting this to log, multiply by the number 2.303. Okay. So, this is the formula. Now, in case of irreversible work, the formula to find out the work done for irreversible work is minus P external into delta V. Okay, you all know how to write the delta V, right? It is V2 minus V1. Final volume minus initial volume. And we have the external pressure multiplied to it, which is equal to the work done in case of irreversible process. Okay. Now coming to the third one. Third is free expansion. In case of free expansion, the work done will be 0 because it will expand freely. Okay, there is no pressure acting on it. So the work done will be 0. Okay, so the piston can move on its own. It is free expansion. So work done is 0. So these are all the 3 important formulas which you have to note down for all the 3 processes. Reversible, irreversible and free expansion. Okay. So is it clear? Have you all noted these 3 formulas in your notebook? Say yes or no. Yes. All of you? All of you? Only Ayanki and Rakshita has said yes. What about others? Agam is also done. Okay. So others, I hope others also have done it. Okay, fine. Now let's go for the next topic. So we have studied what is work and I have explained you the types of work and we have studied the expression for work. Expression means the formulas to find out the work. Okay. Now let's go for the next topic. Enthalpy and internal energy. Enthalpy, the relationship between enthalpy and the internal energy, we will study at last. We have already studied about this internal energy in the yesterday's class. So now I am going to talk about enthalpy. And later on, I will give you one relation which relates this enthalpy and internal energy. Got it? So moving forward with enthalpy, what is enthalpy? It is the total heat content of the system. It is the total heat content of the system. I may have a system. This is a system. Okay. So the total heat content of the system is called as enthalpy or the heat which is measured at constant pressure. The heat which is measured at constant pressure is called as enthalpy. Both are same one. Okay. The total heat content or the heat which is measured at constant pressure. This is called as enthalpy. So what are the properties of enthalpy? So first of all, the enthalpy is a state function. Enthalpy is denoted by the letter H and it is a state function. What is meant by state function? Which depends only on the initial state and final state of the system. So if I want to find out the delta H, so I have to go for HF minus HI. Final enthalpy minus initial enthalpy. So these two values are enough to find out the delta H. Okay, since it is a state function. The SI unit of this enthalpy is joules. Okay. And also we have one formula which relates the enthalpy and internal energy. H is equal to U plus PV. So this is the formula. Okay. H is equal to U plus PV. And the fourth property is the total H cannot be measured, but only the delta H can be measured. Means only the change in enthalpy can be measured, not the direct enthalpy. Okay, like the internal energy. Yesterday I have told, no? So directly you cannot measure the U, internal energy. You can measure only the delta U. In the same way, you cannot measure H. You can measure only delta H. Okay. I will tell you how to measure delta U and how to measure delta H in the upcoming slides. Got it? So we have some instruments. I will talk about those instruments in the later part of this lesson. Got it? So now you cannot find out H. You can find out only the delta H. So we will get one formula with the delta H and delta U that we will see in the next slide. Okay, next to next slides. So these are the four properties of enthalpy. Okay, it is a state function. The unit is joule. And the relationship between H and U, only the delta H can be measured. All right. So now what is the sign convention? What is the sign we have to use for delta H? In which case it will be positive and in which case it is going to be negative. So that we will discuss next. For exothermic reaction, delta H is negative. Can you tell me why delta H is negative? What is meant by exothermic reaction first of all? Can anyone give me the definition for exothermic? You might have studied this in your 10th class, right? What is exothermic reaction? Very good. If the heat is released, okay, if the heat energy is released from the system, then we call those process as exothermic process. Yeah, if the heat is released, it is called as exothermic process. And in that case, delta H value will be negative. Okay. Then for endothermic reaction, the heat energy is observed. So if it is observed, then delta H will be positive. Okay, here you see the system is observing the heat from the surrounding. So delta H value will be positive. And if the heat is released to the surrounding from the system, then delta H value will be negative. Okay, so this is a sign convention for delta H. Now, the next is the relationship between delta H and delta U. The formula which I have quoted in the beginning of this topic. Okay, the relationship between delta H and delta U. So, delta H is equal to delta U plus delta Ng RT. So, what is delta H? Change in enthalpy. Delta H is called as change in enthalpy. Okay. And what is delta U? Change in internal energy. What is delta Ng? Change in the number of moles of gaseous reactant and product. Okay. Change in the number of moles of gaseous reactant and product. So we have one formula to find out this delta Ng. It is equal to number of moles of gaseous product minus number of moles of gaseous reactant. Okay. Change in the number of moles of gaseous reactant and product is equal to delta Hg. All of you please note down this formula. Okay. And R is the universal gas constant, you all know, right? R is the universal gas constant and T is the temperature. This relation is very, very important because in one of the previous NEET exam, they have asked this relation. Okay, like the question was, which among the following is the correct relationship between delta H and delta U? This was the question. Such an easy question, no? Very, very easy question. Direct formula they have asked. So, and it was given 4 marks. Okay. It is not a time consuming question also. If you know the formula, you can directly go for the answer. So, try to memorize this formula. Okay. So, have you all completed this? Shall we go for the next topic? Shall we go for the next topic? Okay. The next is, the next is the measurement of delta H and delta U. I told you, right? We can measure delta H and delta U using some instrument, and that is called as a calorimetry instrument. Calorimetric instruments. Okay. So the process is calorimetry. So first, let's go for delta H measurement and then we will go for delta U. Now coming to delta H measurement. So actually it is measured at constant pressure. Delta H is measured at constant pressure using coffee cup calorimeter. Using the coffee cup calorimeter. Okay, so we have the coffee cup kind of thing and the stirrer is present inside it. And also we have the thermometer to note down the temperature. And we have an insulated stopper over here, like a cap. And we also have nested insulated cups here. Okay, and inside this only we have a sample. Okay, we have the sample here, which is called as a reaction mixture. And accordingly, by doing the experiment, we will find out the delta H. Okay, using the formulas. So you should know the name of the calorimeter which is used to measure delta H. Coffee cup calorimeter. It is measured at constant pressure. Okay, so these are the 2 important points you have to keep in mind. Now coming to delta U measurement. Here the heat is measured at constant volume. Here it is measured at constant volume and the instrument name is bomb calorimeter. This is called as bomb calorimeter. Okay. So these are the 2 points you have to keep in mind about delta U measurement. All right. Bomb calorimeter at constant volume. So this is all about the measurement and the instrument's name. Now we'll go for heat capacity. Heat capacity is the next topic of this first law of thermodynamics. So what is heat capacity? What is the definition of heat capacity? So before moving on to the heat capacity, I just want to ask whether you have any doubts from the topics we have discussed so far or not. Is everything clear for all of you? Students? Are you all following me? All clear? So you should know the flow of the class. Okay. You should not just simply see. You should know ma'am is teaching which topic under this particular topic, how many subtopics she is teaching and what are the formulas she is giving. So you have to maintain a proper notes, especially for this type of physical chemistry lesson, which involves more number of formulas. You have to follow the proper notes. Okay, only that will be helpful for you in the revision part of this lesson. Okay, so otherwise everything will get messed up and you will get confusion at the end. Okay, so try to maintain a proper notes. I already told you, if you need any time to copy any formula or any concept, you can ask me to stop the class and you can get your time and you can get done with your notes. Got it? So shall I go for the heat capacity definition? Yes? All right. So what is heat capacity? It is the heat required to raise the temperature of system by 1 degree Celsius. Okay, so I have a system. So if the system is kept at 70 degrees Celsius and if I want to convert this to 71 degrees Celsius, then some amount of heat is required, right? So that is called as heat capacity. The heat required to raise the temperature of the system by 1 degree Celsius is called as heat capacity. Heat capacity is denoted by the letter C. Okay, it is denoted by the letter C. So now let's study some of the properties of heat capacity. So first of all, it is an extensive property. What is meant by extensive property? Can anyone tell me the definition for extensive property? Yesterday we have discussed, no? What is the definition for extensive property? Very good. Which depends on quantity. Very good. Jane V. Tinskia, student. So may I know your name? Is your name? Is your name? Just, okay. Roshan. Very good, Roshan. So the properties which depends on the quantity or the property whose value changes on changing the quantity is called as extensive, right? So here heat capacity is an extensive property, means the value will change if I change the quantity of the system. Okay, very good. Now the next property is more heat capacity means more heat is required to raise the temperature. More C means more heat is required. So what is the relationship between C and T? It is directly proportional. More C means more heat is required. I have to write like this, no? Instead of T, I can write Q. Heat is required, no? More C, more heat. So C is directly proportional to Q. More heat is required to raise the temperature. So now we do have one more relation in which Q is directly proportional to temperature. And if I remove the proportionality symbol, I have to introduce a constant, and that constant is C. That constant is C. Okay, so Q is directly proportional to C, and also it is directly proportional to the temperature. Got it? Q is equal to C delta T is an important formula. Q is equal to C delta T. The SI unit is Joule per Kelvin. The SI unit of heat capacity is Joule per Kelvin. Okay. So is it clear? All the four properties are clear to all of you? Shall I go for the types of heat capacity? Okay. So let's move on to the types of heat capacity. We do have two types of heat capacity. One is molar heat capacity, which is represented by the letter Cm. And the definition says, heat required to raise the temperature of 1 mole of the system by 1 degree Celsius. 1 mole of the system. You all know what is a mole, right? So, Avogadro number of particles which is present inside the system. So, the heat required to raise the temperature of 1 mole of a system by 1 degree Celsius is called as molar heat capacity. Okay? It is an intensive property. Intensive means the value will not change even if I change the size, even if I change the quantity. Okay, so it is an intensive property and we have one formula, and in that formula you have to include this N because it is related with mole, right? So Q is equal to N C M into delta. Okay, molar heat capacity is equal to heat capacity divided by number of moles. So we know the relationship between the C, right? We know what is C. So accordingly, you can substitute and get the answer. Okay, Q is equal to C into delta T, right? So using that, we can do this. Now, next is the SI unit. The SI unit of this molar heat capacity is Joule per Kelvin per mole. Joule per Kelvin per mole. This is about molar heat capacity. The next type, second type is called the specific heat capacity, which is denoted by CS. The heat required to raise the temperature of 1 kilogram of a system. 1 kilogram of a system by 1 degree Celsius. There it is 1 mole, so molar heat capacity. Here it is 1 kilogram, so it is specific heat capacity. It is also an intensive property, and the formula is Q is equal to M into CS delta T. So here it represents the number of moles only. Okay. Instead of CM, you have to write CS here. And the SI unit is Joule per Kelvin per kilogram. Since it is about the heat required to raise the temperature of 1 kilogram of a system, we have to put a kilogram. Got it? The normal heat capacity is an extensive property, but its types, the molar heat and the specific heat capacity, its types are intensive property. Okay. So clear for all of you? Any doubt from the types and the points we have discussed under each type? No. Okay. Now we'll go for the relationship between CP and CB. So before moving on to the relation, I have given you the meaning of this CP and CB. What is CP? Molar heat capacity at constant pressure, and CV is molar heat capacity at constant volume. Okay, both of them talks about the molar heat capacity. Okay. Now let's go for the very important formulas. So here I have taken two formulas in which delta U is equal to NCV delta T. In one of the previous slide, I have used this formula, no? The same formula it is. So which is equal to QB. Heat exchange at constant volume is equal to N into, N is the number of moles, CV is the molar heat capacity at constant volume into the change in temperature is equal to the change in internal energy. Okay. In case of delta H, it is NCP delta T and it is equal to QP. CP is the molar heat capacity at constant pressure. Got it? So these two formulas are very, very, very important. And CP minus CV is equal to R is another important formula, which has been asked in one of the previous year question. Actually, CP minus CV is equal to NR. This is the relation. Okay. For 1 mole of an ideal gas, N value will be equal to 1, right? So if it is equal to 1, then we will get CP minus CV is equal to R. So this is the formula for 1 mole of an ideal gas. Okay. Is it clear to all of you? So these are the 3 formulas which you have to note down from this point. Finished? Shall I go for the summary of this first law of thermodynamics? So let me summarize. Okay, let me summarize. So first of all, yesterday we have started with the internal energy. So internal energy is the total energy of the system, right? Which is equal to the kinetic energy plus potential energy, which is equal to the internal energy. And coming to the work, mechanical work, it is equal to minus P delta V. So this is the formula we have studied. And for reversible isothermal work, this is the formula. And for irreversible isothermal work, Rakshita, that's what I told you, no? Specific heat capacity means if you want to raise the temperature for 1 kilogram of a substance, it is specific heat capacity. Molar means to raise the temperature of 1 mole of the substance. 1 kilogram is different from 1 mole. Right? So this is mass. Kilogram means it is mass. Moles means that is a different term. Okay? Yeah. So we also have a relation, right? Number of moles is equal to mass by molar mass. So this is number of moles. This is the mass. You will get the mass only if you multiply the number of moles and the molar mass. But you can find out the number of moles by dividing the mass and the molar mass. Got it? Yeah, coming to the work. For irreversible isothermal work, it is minus P del B. For free expansion, work is 0. So these are the 3 formulas which I have asked you to note down. And coming to heat capacity, C is equal to Q divided by delta T, or Q is equal to C into delta T. Okay, so this is a relation which we have studied now. And for molar heat capacity also, I have given you this relation. Here you have to include N, and here you have to include M. And at last, the relationship between Cp and Cv is equal to, Cp minus Cv is equal to Nr for N mole of an ideal gas. For N mole of an ideal gas, this is the formula. For 1 mole, it is 1R. For 2 moles, it is 2R. Okay? This is the ideal gas relation for heat capacity. So these are all the formulas we have discussed in the first law of thermodynamics. Okay? So now moving forward with this, I'm going to give you some previous year questions from the topics which we have discussed so far. Okay? So all of you try to find out the answer. Okay? So here is the first question. Previous year question from this lesson. Which among the following option is the correct relation between change in enthalpy and change in internal energy? Very easy, right? Just now I have told you and I have shown you. What is the answer? Which is the correct relationship between change in enthalpy and the change in internal energy? Delta H and delta U. All of you should try. It is a very easy question. Very good, Rakshita. Are you all agreeing with the Rakshita's answer? Is it option A correct? Roshan is also going for option A. What about others? What about others? Is option A correct? So in all the options, you just see, they have just made a slight change in all the options, which will confuse us. But if you are very clear in the formula, in memorizing the formula, you can get the correct answer within a fraction of second. Okay. Option A is the correct answer for this question. Very good. Now let me go for the next question. The question says that 1 mole of an ideal gas at 300 Kelvin is expanded isothermally from 1 liter to 10 liter. Okay. Delta U for this process is. What is the answer? R value is given, temperature is given, volume is given. We are asked to find out delta U. Number of moles is also given. Number of moles is also given as 1 mole. Okay. Number of moles is given, temperature is given, and it is expanded isothermally. Okay. Isothermal expansion it is. So find out the value of delta U. Find out the value of delta U. Has anyone got the answer? All of you try. Not even a single student has got the answer yet. It is very easy actually. See, listen, all of you. Delta U is equal to NCV delta T. So I have given you this formula, right? And here you see the process is isothermal. It means temperature is constant. Isothermal means the temperature is constant. If the temperature is constant, then delta T is equal to 0, right? So this delta T goes to 0 and 0 into anything is 0. Delta U is equal to 0. So the answer is option A. Okay. Delta U is equal to 0 for this question. Is it clear? You don't have to substitute the number of mole, temperature and volume. So directly by looking into the isothermal formula, you can get the answer. Is it clear for all? Any doubt? Shall I go for the next question? Yeah. So coming to the next question. Okay. Which of the following pressure volume curve represents the maximum work done? Which among the following option represents the maximum work done? So here which concept you have to use? The maximum work done is equal to the area under the pressure volume curve. Very good, Rakshita. Again, option B is the correct answer. Why? Because in option B only, the area under the pressure volume curve is more. Okay. So in case of A, it is less, and in case of C, we don't have the area at all. And in case of option D, the area is very, very less. Yeah. Area is more in case of B. So that's why the maximum work done is, being done on option B. Okay. Next question. Which among the following is the correct option for right relationship between Cp and Cv for 1 mole of an ideal gas? Very good. It is option C. Yeah, it is option C. For 1 mole, it is Cp minus Cv is equal to R. Okay. Very easy questions, right? So straightforward questions was asked from this lesson. We also have some numericals that I will solve in the later part of this lesson. So these are all the straightforward questions. So I'll go with one more question for today's session and then I will wrap it up the session. Okay. So this is the last question. The correct option for free expansion of an ideal gas under adiabatic condition is. The correct option for free expansion of an ideal gas under adiabatic condition is. So for free expansion, what I told, the work done will be equal to, for free expansion, the work done will be equal to 0, right? For free expansion, the work done will be equal to 0. This is what we have studied in the 3 formulas of work done. Okay, W will be 0. So either option B or D should be the correct answer. And also the question says that the condition is adiabatic. What is meant by adiabatic? Heat exchange between the system and the surrounding is 0. Adiabatic means Q is equal to 0. Heat exchange between the system and the surrounding is 0. So those are called as adiabatic condition. So W is 0, Q is also 0. So it is given only in option D. So option D is the correct answer. I'll tell you why delta T is 0. We know that delta U is equal to Q plus W, right? So both of them are equal to 0. Q is also 0, W is also going to 0. It means delta U is 0. So when do we have delta U as 0? We have N is equal to N, delta U is equal to NCV delta T, right? When this delta U will go to 0? It will go to 0 only when delta T goes to 0. Okay, so that's why delta T is also equal to 0. I hope it is clear to all of you. Thank you so much for attending the lecture. So kindly give your feedback in the poll which I am launching now, and then you can get ready for your next class. Do any of you have any doubt from today's session? No? Okay. Thank you so much, students. Thank you so much for listening.